the first thing I should do is I should probably clean up my setting out for something which sort of floated over before, but didn't talk about in much detail, which is that suppose we have some function, right? And it's, let's go with 2x. I think that's what we were working with before. Okay. So we said that one of the conventions for how to write the primitive of lowercase f is to write it as capital F, right? Good. Okay. Now, just to revise, right? We know that one function only has one derivative, okay? But it's got a whole bunch of different primitives, a whole family of them, okay? So we distinguish between them by adding a constant. Do you remember that? Nod slowly at me if this is ringing a bell. Yes? Okay, good. Now, I forgot to mention that. I was a bit naughty. You add a constant on, right? Remember, we called this an arbitrary constant.
You have to say C is an element of
Yeah, so because it really can be anything, like its value can be anything, that's what we mean by arbitrary. You have to state, well, okay, well, what kind of number is it, right? So really, you should say off on the side here, and it's a bit like, you know, in general solution, where you're like, okay, sine x is equal to a half. And I said, well, okay, let's revise. What is the general solution for this? Do you remember? Sine. Yeah, okay, good. N pi plus switchy thing. Yep, good. Times, in this case, what is it?
Pi on 6.
Okay, thank you. Right? And because you've introduced your n, right? That's why we had to say here, well, okay, n has to be an integer. Yes, can't just be any number. In the same way, come in.
High five.
Who do you need?
High five.
Huh? Wow, padlock and all.
Thank you. Sorry, miss.
It's fine. What do we say? Okay, so like we had n here, we describe what rules it obeys. Okay, you do the same thing for C. Okay, so every time you find the primitive,
You do the wiggly brackets.
you don't have to do the wiggly brackets, but the alternative is you say where. Okay, because you've got to say this is true where. I prefer curly brackets, and they're fun to draw anyway. So I'm going to go back to. No, they just take some practice. Okay, so C, we tend to say it's a real number. Okay, that's it.
But can't it be an imaginary number?
Well, you guys are 3-unit students, so we're going to go with real numbers for now. Okay, so
But isn't
yeah.
that not technically mathematically correct?
Well, it is for the purposes I have in mind, because later on when we do move on to the special I word,
No,
okay,
I mean,
I'm
it's
only regarding it
correct,
with
but
respect to
not
real numbers.
Most is correct. Like it's correct,
Well-
but there's more other correct things not included.
No, for reasons that are hard to explain unless you extension 2. So that's where I'm going to leave it. Okay, sorry. Now, here's what I'm trying to do. I'm trying to evaluate the constant, right? So at the moment, it can be any number, which is why I've got this whole family of graphs that all equally can claim to be the primitive. Okay. So what would I need to be able to work out? Well, okay, what's the number? What's the
You need
number?
the points.
Right. So if I can know, like the difference between all of these is the path that it traces out, the points that it goes through.
Or the
Okay.
directrix.
So
Or focus.
kinda. So if I know that this primitive goes to a certain point, like say this one, okay, let's say it goes through there, and I give you its coordinates. Suppose it passes through, I don't know, what does that look like?
1, 1.
2, well, it doesn't look like 1, 1 to me.
2, 4.
Well, I think it's sort of a bit, I'm gonna go 5, just to be interesting.
What's the story at the origin?
Oh yeah, that's a bad one. Let's go with this one. Let's go with that one, because that's already that one's already got a point. Right, that doesn't look like 5 anymore. Let's make it 7. Okay. So now that I know it goes to a point, right? It can't be all these other ones. It must be this one and this one only. Okay. So I can use that fact to evaluate what the constant is. Okay. So here's the way I would do it. You can do that later. You can do it later.
Oh, sorry.
Thank you. Suppose. Let's rewrite this, by the way. I might not write it like that. I might say this is dy on dx. Okay, which would make this y. So how do I evaluate what the constant is? Well, I say when, this is what the coordinate 2, 7 means, right? When x equals 2, y equals 7. Yes? So I'm going to take that and I'm going to pop it into this line, y equals x squared plus c, right? So that's going to give me 7 equals 2 squared plus my constant, So you get 4 there, and you card it over, so you get 3. So now I have my equation for y. And it's not an arbitrary constant anymore. I've evaluated it. That's all. Yeah?
We have to change it back to the x.
Well, it depends on what they give you the question in what terms they give it to you originally.
They gave me
So if they gave it to you in just f's, okay, just f's. So they might say something like, find f of x where, how would they say it? They would say where f dash x equals 2x, and instead of giving you coordinates, because there's no x and y, there's x and there's f, they would say f of, what I have, 2 is equal to 7. So that's the equivalent of saying it passes through 2 comma 7. Okay? And then you would go about it in the same way, and you'd work out exactly the same constant. Okay? But it's important, you can't skip this step. You can't leave out the constant, or like say, okay, I can tell what the constant is right away. You've got to pop it in, say it's some arbitrary thing, and then evaluate it properly. These steps here, right, they're quite important. Later on, it won't just be a number when you're doing like some, who knows what it actually signifies. Later on, when it's like rates of change or exponential growth and decay, this will mean like a population or some level of radiation or a temperature or something like that. Okay, so even though it's just a number, in our case, it'll become really important later. That's why you can't just skip this step. Okay.